Okay, so thanks everyone for coming. Like Chris said, my name is Kerby Shedden. I'm over in the staff department, but I spent half of my time with Chris over at C-Star. Well, Chris is there half the time, but I'm half the time theory at least. And I recognize most people here, not absolutely everyone, but I recognize most of you. So I hope we can have this be very casual. I didn't have a really clear sense of like what kind of talk to give here. I suggested the topic and Chris said, okay. And didn't stop me anyway. And this is not supposed to be like a research talk, although maybe just by habit, it kind of got more looking like a research talk than I intended it to. But I can skip over stuff. I probably got more stuff than I can cover anyway. I can skip over stuff. But obviously, I think what would be most useful would be more of like a high level overview of this subfield that I assume that people don't have much exposure to. And I have a few examples at the end, and probably the examples at the end that are most interesting. So the worst thing would be if I got bogged down in the technicalities and didn't get to the examples. So make every effort to keep that from happening. Just want to make sure so that people online can hear me on Zoom. I guess.
Yes, we can.
Thank you. And feel free to this can be very informal. So for those online as well as those here, just feel free to just speak up. You don't have to raise your hand or anything. Just speak up if you have a comment or a question. And we can, like I said, we can skip over stuff. We can dwell on things, and you can basically take this wherever you want. Okay, so this talk is about a branch of statistics that is has a decent history behind it and quite a bit of high quality, rigorous work behind it. Just a second, I'm trying to figure out how to advance the slide here. There we go. But nevertheless, I'm sure it's not widely taught, or hardly taught at all really in course academic programs. And so it's something that you know about if you work in this area, and you may have barely any familiarity with it if you don't. But it has an interesting history behind it. So I'll talk a little bit about the history, and it has some interesting connections to other areas. I'm not here as an evangelist. This is not my main thing. There's out of full disclosure, the reason I know about this area is because my PhD advisor was one of the main figures behind it, but I actually didn't work in this area at all in my PhD work. But I became aware of it through that connection. And I've just kind of followed along ever since then. And I've always thought that maybe it'd be nice to actually make use of this methodology in appropriate ways. And here and there I do. And recently I've actually started working in this area with my former postdoc in Taiwan. But I don't have like a bunch of history and contributions to this area myself. I just kind of followed it along as it's evolved. I guess it was born. I'll talk a little bit about the history, but I guess it was born in the early 90s. You can even say it was born in the 70s, but really it was born in the early 90s. And it's kind of continued since then. The top journals publish maybe 1 or 2 papers a year in this field. So it doesn't compete with a lot of other areas where there might be dozens of papers published each year. But it never goes away. So I feel like it has some kind of staying power. It's worth thinking about. And even if maybe I can't remember if I already said this, but even if you don't use it, it gives like a fresh understanding of just regression in general, non-parametric regression in general. So it kind of helps you understand how deep learning works to some extent, or it helps you understand how generalized additive models work. So it's kind of nice to know about, even if you don't use it. Okay, so there's some boilerplate stuff here at the beginning. So let me just kind of get through this. So we're talking about regression here. So when we talk about regression, the notation I use throughout is this is a technique for non-parametric regression. So I want to use sort of notation that's appropriate for non-parametric regression. So we're talking about this object called the conditional mean function, which is the object that most all of regression analysis is interested in. And this is just an estimand in and of itself. This in and of itself is not a generative model. It doesn't describe the entire probability distribution that represents the data. It's an estimand that captures a lot of the relevant information in the data. And so it's reasonable to try to estimate this thing. If you want a generative model, you can potentially have a generative model like this, but you won't see this type of y equals something equals epsilon notation again throughout this talk. So it really boils down to like, what's the most we can learn about this object here non-parametrically? Okay, so why do we want it to be non-parametric, at least sometimes? So this is the parametric linear representation of that conditional mean function that we all are extremely familiar with. So if you want to keep it simple, you can model the conditional mean function as a linear combination of the explanatory variables. And so in what exact sense is this thing restrictive? In what exact sense? People talk a lot about flexible regression. So in what exact sense is this thing not flexible or restrictive? Well, if you really want to be precise about it, the way I think about it anyway is that there's two important restrictions placed on this representation. One is that it's linear and the other is it's additive. And I think it's important to understand that linearity and additivity are different things. You can be linear but not additive, you can be additive but not linear, you can be both, you can be neither. So essentially what linearity means is that if you hold all but one variable fixed and modulate one of the variables while holding the others fixed, that the regression function travels the same distance regardless of the origin of the one variable that you're manipulating. So essentially it means that the partial regression relationship of y on xj is linear when holding all the other x's fixed. So that's what it means to be linear. And additive essentially means no interactions, but to put a little more formally, it means that if you hold all but one of the variables fixed and manipulate one, the manner in which the expected response changes doesn't depend on the specific values to which you fix those other regressors, right? So additivity doesn't make sense unless you have at least two covariates. So we're thinking here regression settings where you have at least two explanatory variables. And these things can be viewed as putting constraints on derivatives, but we don't need to worry about that too much right now. So linearity and additivity, those are the two structural assumptions, if you will, built into the basic linear model that was in wide use, at least up until the 70s or so. And then starting in the 80s and 90s, people started to become more interested in, I'm not going to go through this slide in detail, more interested in flexible non-parametric regression. And so in that era, let's say in the 80s, the thing that became sort of in vogue was this general non-parametric regression or local polynomial regression or scatter plot smoothing or LOAS. There's different terms that people use to refer to what's essentially this idea, which is to form these little neighborhoods in the covariance space. And then within the neighborhoods, you have a linear model. But as you move the neighborhood, the parameters of that linear model can change. So essentially you can represent anything, at least anything that's smooth. And some people like to think of this as almost like a Taylor's theorem approach to doing regression, which is local representation, which is polynomial-like in any corner of the covariance space, so that local representation changes as you move your origin around. So it's a great idea. It works in theory. It sometimes works in practice, but if you haven't noticed, you don't actually see all that much. And the reason is because this notion of the curse of dimensionality. So as the dimension of the covariance space X gets larger could even be like 4 or 5, it's relative to the sample size, but you need enormously large sample sizes to even come close to filling, say, 10-dimensional space with any reasonable amount of data. So these very non-parametric methods, overly flexible methods, essentially break down when you have anything close to like a moderate or high dimensional dimension to your data, a moderate to high dimensional number of variables. And that's called the curse of dimensionality. You still hear people using that term. In my sort of learning process, getting my PhD in the 90s, this was the term that you heard all the time. It's like the curse of dimensionality. It's the key thing that people want to work around. And that led to an explosion of interesting ideas. I would tag most of these as having originated from the late 80s to the early aughts, when people were trying to be creative and try to think about new ways to do what they call flexible regression. Flexible regression, which is a sort of a sly way of saying that you can't be fully non-parametric unless you have a sort of unreasonably large amount of data. So you need to put some structure on the model, but you don't want to put so much structure on the model like the classical linear model where everything's linear and additive. So what kind of methods can people come up with that either by regularization or by explicit structural constraints put just enough restriction on the regression problem so that you can estimate things with however much amount of data you have. And ideally, these methods are adapted so that they automatically become more flexible as the amount of data grows. So that turns out to be a tall order. And I don't think the project is complete or that this goal has been reached, but there's some nice ideas that get us a decent amount of the way there. So I'm not going to enumerate these, but these are some of the ideas that most of these I'm sure you've all heard of, and then you've probably used these methods more than I have. These are some of the ideas that date to this historical period, the 90s and early aughts. And things kind of went off in a different direction after that, which isn't so much relevant for today. And one of these, and probably not the most, well, certainly not the most well-known, but one of these methods that I would put in this historical frame is the so-called dimension reduction regression. Part of the reason it's not well known is maybe just because it doesn't have a catchy name. Maybe there's a better name for it, but I'll call it dimension reduction regression, or DRR. It was one of the methods that, like I said, emerged in this era to try to produce practical, flexible regression methods that can be used in theory or ideally for daily practical data analysis, not just something that's elegant theoretically, but this is supposed to be a useful technique. And it emerged in that era. So let me talk a little bit about the main idea behind dimension reduction regression. So let me start with the idea of a single index model. So this is a term you may have heard before. So a single index model is a way of putting a fair amount of structure on the regression function that you're trying to estimate. So here's your regression function again, the conditional mean of y given x. And you put the structure on it in which you have a link function g, and then inside of the link function you have an index or a single index or just a linear predictor if you prefer. So a linear combination of the covariates. And the linear combination of the covariates then gets filtered through this potentially nonlinear function g, which is unknown. So this could be viewed as a type of semi-parametric analysis where the linear part is parametric, the finite dimensional parameter beta that governs the linear predictor, and then there's essentially an infinite dimensional parameter g that links the linear predictor to the response. Right? This may look a little bit like generalized linear models, which is not the topic of today's talk. That comes from an earlier era. The GLMs were the hot new thing in the 70s. So we're about 10 years beyond that here. So in generalized linear models, you know the G, or you pretend that you know the G, but in this dimension reduction regression, you treat the G as an unknown, essentially as a nuisance parameter. And then another important aspect of GLMs is that you try to gain efficiency by exploiting the invariance relationship, which isn't really something that comes up directly in dimension reduction regression. So the goal of a limited example of dimension reduction regression is to estimate models like this semi-parametrically without making any assumptions or strong assumptions on G, and then trying to recover estimates of the coefficients beta. And an interesting thing is that estimation of G and estimation of beta turn out to be almost orthogonal, since you can estimate beta without even coming up with even a working estimate of G. That's maybe a little bit surprising.
There's got to be something you have to do to make it identifiable.
The G?
I mean, it seems like if you double G in some sense, you can have beta.
Right, exactly. So G, their beta is only identifiable up to, I have this in a later slide, but beta is only identifiable up to norm, and even then up to sine flip, right? So yeah, constant multiple of beta would just get absorbed into G. So beta, for all practical purposes, is a unit vector, and even then it's not identified because you can flip it by plus or minus one. So it's really the subspace spanned by beta that's identifiable, which is a nuisance to be sure. Absolutely. So I'm not going to dwell on this, but an interesting sort of antecedent of all this work was that David Brillinger, very famous statistician, is still alive, back in 1977, almost as like a side comment in a paper on time series, proves theoretically that in some circumstances you can essentially ignore G, ignore the possibility that G is there, and simply regress Y on X, even though you don't really believe that Y is linear in X. If you believe in this model, instead of this model without the G, you can regress Y on X, and you'll still recover what the only thing you could ever hope to be able to recover per the discussion we just had, which is essentially the space spanned by beta. So Brillinger proved that in 77. As far as we know, that was never known before. And an interesting thing about that result is that it's very flexible in one sense, but surprisingly non-flexible in a different sense. So what do I mean by that? It's very parametric in one sense, but surprisingly non-parametric in another sense. So it's very non-parametric in the sense that it assumes almost nothing about G, and it assumes almost nothing about the conditional distribution of Y given X, which is usually where you're focusing your effort when you're talking about regression analysis. But somewhat surprisingly, you need to put fairly strong, at least Brillinger needed to put fairly strong conditions on X itself for this to work. The distribution of X has to be, well, in his case, it has to be Gaussian, which we don't normally want to assume that our covariates in our regression analysis are Gaussian, right? But this was, like I said, it was a side point of his paper, so he didn't push it very far. But at least he did introduce this notion that if X is Gaussian, then you simply regress Y on X as if there was no link function, and nevertheless you recover the only thing you could ever hope to recover, which is a unit vector spanning this subspace that we now call the sufficient dimension reduction subspace. It's like you only need to know about X through its projection and direction data to know everything there is to know about Y. Okay. So that's what Brillinger proved, but it's a bit peculiar that X has to be Gaussian. for this to work. And I have here a simulation study that shows that it's not strictly speaking Gaussianity that's required. And this was proved later theoretically that you only need an elliptical distribution. And in some cases, you can get by with less than that. And the weakest condition that I know of for this notion to work is that you need the so-called linear conditional mean condition to hold, which I won't try to delve into here because it would take too much time. But if the LCM condition doesn't hold, if you have like a, say, uniform, I don't know if you can even read these legends, you probably can, but if you have like a uniform distribution on X or an exponential distribution, or worse yet, like a mixture where different components of X have different distributions, you have very strong violation of the linear conditional mean assumption, and under certain, even then, under certain pathological choices of the length function, then things can be way off. So I don't want to leave the wrong impression here that you can always regress y on X and claim to be robust to the presence of this length function, but in many cases you can, and that was I think a bit of a surprising result. So that result sat on someone's desk, I guess, for a couple of decades. And then maybe in the early 90s or late 80s, I think it was late 80s, very late 80s, someone sort of revived this mode of thinking and started thinking about multi-index models, which are now a kind of a hot topic in statistics, and asked whether or not there's some more generalized way to approach regression with possibly multiple indices that kind of is, as in some sense, gives you a flexible spectrum of analytic approaches that can range from a very restrictive single index model all the way up to a model that is essentially equivalent to this non-parametric approach that suffers so badly from the curse of dimensionality. So the idea of a multiple index model is that you don't just have one of these linear predictors, you have Q of them, where Q is an unknown value that would be potentially as small as 0 if Y and X are independent, or as big as P if there's essentially no structure to be exploited at all. So we have, hopefully we want Q to be fairly small, say 2, 3, maybe 4, gets a little bit unwieldy after that point. And so the idea is that there might be 3 or 4, say, linear combinations of the X's. You need to know all of these linear combinations of the X's, but you don't need to know any other linear combinations of the X's. So this starts to feel a little bit like factor analysis, right? Where you try to say that the variation in X without there being any response variable Y to even discuss, that the variation in the X's or the important variation in the X's, whatever that means, is captured by a limited number of quote-unquote directions, and the betas are the directions here. Okay, so this opens up a whole new realm of research starting in the late 80s, is can you estimate these beta vectors, and it just as Chris said earlier, it's not necessarily the beta vectors, but it's really the span of the beta vectors that you can uniquely identify. But in practice, you just estimate the beta vectors and acknowledge that that's one of infinitely many different bases that span the same space. So can you estimate the span of the beta vectors, the so-called sufficient dimension reduction space, non-parametrically? And what I mean by non-parametrically or semi-parametrically is without specifying the form of G. If you specify the form of G, then you can do this by actual, there's lots of ways to proceed. But if you don't specify the form of G, it's not obvious that it's even possible to estimate the betas non-parametrically.
May I ask?
Yes.
When you don't specify the form of G, how do you do the regression?
Well, let me show you how you estimate. It's a little bit of a trick. It's not curve fitting. That's the thing. It can't be curve fitting, because to do curve fitting, you need to know G. If you want to minimize like Y minus this thing squared, as if you were doing curve fitting, I would totally see where you're going from. So you have the estimation of the betas is indirect. It's not by curve fitting.
So are you going to show an example of that?
I am.
Okay, great.
Before I do that, just very briefly, this is not as important, but this is building on Brillinger's idea again. So here's just to make it concrete, here's an example of a 2-index model, right? So I've got 5 covariates here. I don't say that anymore, but X1, X2, X3, X4, X5 are your covariates. But those 5 covariates only relate to the mean of Y via 2 linear combinations, the U linear combination, which is X1 minus X2, and the V linear combination, which is X2 plus X3. But then U and V relate to Y, or the mean of Y, by this polynomial expression. So you can't further collapse U and V to a single vector. So you need U and you need V, but you don't need any other information about X once you know U and V. So this is just an example of a 2-index regression model. And the rows, the columns of B span the so-called SDR space as I defined it before. Now, if you try to do Brillinger's thing, of course it can't work. because least squares can only ever give you one direction. But at least you might ask, well, does the one direction it gives you at least fall within this column space of B? And just numerically, it looks like it does. So that if you regress Y on X using ordinary least squares, you get essentially like 2.7 times X, 1 plus 2.9 times X2, let's just call it X1 plus X2 up to norm. And nothing else is significant. So the other variables, the other coefficients are arguably no different from 0. So it gives you 1, 0, 1, 0, 0, 0. Oh, I said there was 5 variables before, there's actually 10. Made it a little bit harder. And that vector 1, 0, 1, 0, 0, 0, 0 is obviously in the span of the column space of B. It's the first column plus the second column. But obviously you can never recover all of the SDR space just by doing ordinary squares. So that's the challenging question methodologically, is how do you recover the full SDR space, or as much of the SDR space as you can? Obviously, we're not going to get there using ordinary squares. Let me just skip over this because I can see we're going to run short on time. I also want to, before I'm going to get back to the question, how do you actually do this here in a minute? A different style of notation has emerged over the years, which you see primarily in this field and not so much in other fields. And so I think it's actually a very elegant way to non-parametrically describe what you're really doing inference on when you study a regression model, which is conditional independence. So the way you express in this somewhat eloquent notation that the column space of B is you only need to know about X through its projection onto the column space of B. The way you express that is through the statement about conditional independence. So you say that Y is independent of X given B transpose X. So B transpose X projects X onto the column space of B. So this here might be like a Q dimensional vector. This here is a P dimensional vector. Q is generally much less than P, at least for this methodology to be useful. So what we're saying is that I only need to know a few linear summaries of X in order to have absorbed everything I need to know about Y. Everything else in X is unrelated to Y once I condition on those few linear combinations of X. Right? So it has a little bit of vector analysis here, the way I see it. Okay. I'm gonna skip that second line. So once we start talking about taking linear combinations of X's and using them for some downstream purpose, you probably start thinking about classical dimension reduction. Now we're way back in the 1930s, like canonical correlation analysis, linear discriminant analysis, and hoteling and all that stuff. So we all know that one way to fit a regression model, especially if you have a lot of covariates, is to so-called principal component regression, PCR. So in PCR, you do a principal component reduction of X to achieve factors, and then you include those factors as your covariates. And that method can, in practice, work quite well, but theoretically, it sort of has nothing going for it, right? Because this is the standard critique of PCR, is that there's no reason, the PCR only looks at X when deciding which directions to preserve. So there's absolutely no reason why the directions in the X space that are most informative about preserving the information in X are also the directions in the X space that are most informative about Y. You can think of examples where there's completely the opposite. Like the directions in X that explain the most variation X are exactly the opposite of the direction in X that explain variance Y, and vice versa. Now it does happen in practice that, and I don't know why, but it does seem to happen in practice that the principal components often are pretty good summary indices for regression analysis. So there's no mathematical reason why that should happen in general. It just happens to happen in practice, at least in my experience. So again, theoretically, there's nothing going for principal component regression, although in practice it works reasonably well. The goal here, and I still haven't gotten back to the question, which I will, is to identify B in some efficient and optimal way. So can we identify the right B, no bigger, no smaller than is necessary for this statement about conditional independence to hold? So certainly principal components regression is not going to do that for us. It's going to sometimes work, but other times it'll give us too much, other times it'll give us too little. There's no reason why it should work in general. And I'm going to talk just a little bit about Fisher's linear discriminant analysis, a very classical technique. Yes.
Okay, so the previous slide, Y is independent of X conditional on X conditional on beta prime X.
Yeah.
I'm having trouble with that concept that X conditional on beta prime X.
Was, sorry, maybe parentheses should be there to make it more clear. So it's, the statement is that y is independent of x. Given, is it, oh, I think you were putting the parentheses over here.
Oh, that's what you were saying.
Yeah, so by conditioning on beta transpose x, these two things now become conditionally independent of each other. Right, it's not, I hear you, it's not to be read like this. That was what I was told.
Oh,
The parentheses go to the left. Does that help?
yeah,
Any other questions before I move on?
Basically, once you projected X out of the column space of beta, there's no more information. They'll help you predict Y.
Right. No, maybe a more tangible way to think about it is you can always partition the p-dimensional space into the subspace spanned by E and the subspace spanned by say D perp. And so it's basically saying that D perp X contains no information about Y, Dx contains all the information about Y. Okay, so I was going to say a little bit about Fisher's LDA, just because I think it warms you up to the idea of how the estimation algorithms in this area actually work. So maybe I will just spend a minute or so on this. I think this is stuff you've seen before. So this is Fisher's LDA, the irises, the methodology that was used famously with the irises. So Fisher proposed to do something like this type of dimension reduction regression, but in the setting of a nominal Y, a categorical Y, this is a bunch of labels, but we're not really interested in that today. We're mainly focusing on the setting of a quantitative Y. So when you have a nominal Y, like the irises, the 4 species of irises, you can consider the law of total variation, which tells you that the variance of the features, which remember is things like sepal length, petal length, measurable characteristics of the flower and the leaves and so on in the flower, or the parts of the flower. The covariance matrix of that random vector can be decomposed into the mean of the conditional covariance plus the covariance of the conditional mean, where you're conditioning on the species. Right, so the marginal covariance of X is essentially the within covariance plus the between covariance. Now, logically, it's only the between covariance that would be relevant if your goal is to understand the differences among the flowers, right, or among the species. Okay. So there's actually 2 ways of doing linear discriminant analysis, you may recall. One is more model-based. In Fisher's LDA, there's no model in sight, and it's all about moments. And that, again, is going to be more evocative of what we're going to do here in a minute with the dimension reduction regression. So Fisher proposed this maximizing the so-called Rayleigh quotient, in which you essentially try to find a linear projection of X with coefficients in V, such that the between group variance in that one-dimensional projection is maximized relative to the within group variance in that one-dimensional projection. And it turns out that can be calculated very easily by solving generalized eigenvalue problem, this eigenvalue problem right here. So it's very easy to do, at least with modern software. Fisher didn't have access to modern software, so now they were still thinking about this way back then. So keeping that in mind, the goal now is to do something, and one thing I didn't say is that the generalized eigenvalue problem here, you could have, in general, like the eigenvalues will never be 0. So if an eigenvalue is 0, it means its corresponding eigenvectors contains no information about the between group variation of the species. So you'd want to essentially throw those directions out. But in practice, none of the lambdas are going to be exactly 0. So you have to do this thing like you're often doing in classical multivariate analysis, where you decide how big does lambda need to be before you want to pay attention to the directions in the corresponding eigenvectors. Right, but the point here is that it's not just one direction, right? You could have, 2 or 3 eigenvectors with large eigenvalue, and then another 2 or 3 eigenvectors with small eigenvalues. And so the span of the eigenvectors corresponding to the larger eigenvalues would be sort of like this notion here, right? It would capture the relevant information in X about Y, and then the span of the eigenvectors with small eigenvalues would be effectively ignorable. Okay, so how do we do something like that, but with a quantitative response, more like in a traditional regression setting? So this is just, let me skip over that. Let me skip over this too. Sorry, we can come back to this, but let me just get some so-called method. So the first method to be proposed to do this in general was this technique called sliced inverse regression. And sliced inverse regression was published in JAWS, I think, in 1992 or so. And I don't think that you can analogize it to LDA, or you can not analogize it to LDA. There's a couple different ways of sort of thinking about how the sliced inverse regression idea works. I presented the LDA idea here, but we can't apply LDA directly because we don't have a nominal y, we have a quantitative y. So a natural thing to do would just be to like essentially cluster your y's into bins and then treat them as if they're nominal and then you fish LDA. Now that's not exactly what sliced inverse regression is, but if that's an easy way to think about it, I have no objection to that, okay? So what sliced inverse regression really tells you to do is it says sort your data, this is where well, I'll tell you in a minute. Sort your data from according to y. So because y is a quantitative scalar valued variable, you can sort with respect to y. There could be some ties, and we don't need to worry about ties right now. So you sort your data with increasing y, and then you partition this sorted sequence of observations into slices. And it's not necessarily that important how big the slices are. Roughly speaking, you usually want to have around, if you have a sample size of n, you want to have around root n slices, each of which has around root n observations in it. But there's considerable leeway there. It's not that the results aren't that sensitive to how the slicing is done. Okay, but the key thing is you slice them in the order in which the y's are sorted, right? So that any two y's in the same slice are close together, right? So you can probably see where this is going. You now use those sorted y's. I didn't write this in my slides, I write it on the board, to produce essentially what is a non-parametric estimate of the conditional mean function. To say in I, right? So as long as y is in some interval I, then you can estimate the conditional mean of x given y just by taking the sample mean of the x's whose y's fall inside of I, right? So you get one of these for each slice, I'm calling it m, up there, and then you take the sample covariance of those sample means. So this is the way to estimate the between group variance matrix empirically using very, very basic like method of moments type thinking. Okay. There's some very interesting theoretical work again on the slicing, and Tyler Shing is one of my colleagues that proved a very interesting property of the slicing that we can talk about later if you want to get into that. But let me not get off on that tangent at the moment. Okay. So you do basically the simplest possible thing that you can, given that your y's aren't presented to you as labels, they're presented to you as quantitative values. You create labels out of them. Are you raising your hand or
No.
And so what is the inverse about here? So there's the slicing, and hopefully I made that clear, but then there's the inverse. What is the inverse about? So the inverse is about the fact that what I'm looking at here is the mean of x given y, which should strike you as a bit odd given that y is a response variable and x is our explanatory variable. So normally when you have that type of regression set, you want to look at the mean of y given x. So this is an inverse regression in the sense that you look at the means of x given y, not the means of y given x. And yet you're still, at the end of the day, you're still aiming to learn about the mean of y given x. I haven't changed the goal to just talk about the mean of x given y. The goal is still to learn about the mean of y given x, but we can learn about the mean of y given x by doing something slightly clever with these conditional means of x given y. Okay. So we have to figure out how to learn about the forward regression function given information about the inverse regression function. That's essentially what this boils down to. Okay. And one way to think about this also, like I said, there's several different ways to think about what sliced inverse regression is actually doing. But one way to think about it is that the conditional mean of x given y, because y is scalar, is a parametric curve, right? As you vary y, then the mean of x given y traces out some like form, some piece of string wandering around in RP, right? P I'm using as by convention and dimension of the covariance space. So as you vary y, the mean of x given y wanders around in RP. And if it happens to live exclusively in a lower dimensional subspace of RP, it turns out, and it's actually not obvious, but it turns out that that subspace coincides with this thing I defined earlier as the so-called SDR space that meets the conditional independence condition here. Okay. So that was kind of the big theoretical insight here, is that there actually is a connection between the conditional mean of x given y and the sufficient dimension reduction space with the conditional mean of y given x. There's a connection between the two. With the caveat that dates all the way back to that paper of Brillinger that I referred to earlier, is that X needs to be, at least, it needs to satisfy this property called the linear conditional mean property, which is guaranteed if X is Gaussian or even elliptical, but isn't guaranteed in all cases. And that led to a lot of work trying to understand like the robustness of this technique to violations of LCM, and that work continues to this day. There was an interesting paper published last summer on testing for LCM. So it's an ongoing concern about this methodology. I think the one thing I can say that might put your worries to rest a little bit is that what typically happens is when LCM fails to hold is you still identify part of the SDR space, but you don't identify all of the SDR space, but you don't identify stuff that's out of the SDR space. Right? So you're not like, you're making like a type 2 error, not a type 1 error in some sense. Right? So essentially what the sliced inverse regression boils down to, and this is finally the answer to the question about how does this actually work, is that by taking the inverse regression perspective and looking at these conditional moments of X given Y, and then taking the dominant eigenspace of this particular conditional moment of X given Y, and hoping that the LCM condition holds, then you can recover a basis that spans the so-called SDR space without even having ever said anything about G. The length function G is never mentioned, right? So it's obviously in there somewhere. We don't need to estimate G and then plug in an estimate of it. That's always considered to be like bad form in this field for some reason. Like estimate, there are techniques in this field that estimate G and plug in an estimate of G. Those are always considered to be kind of violating the defined directive of dimensional regression, which is you want to try to estimate the SDR space without ever touching G. Okay. So that was 1992, and it turned out that that idea had legs. It could be generalized. So what the so-called sliced inverse regression does is it takes the eigenspace of this matrix M sur here. This is the population version of the matrix we're working with, and it asserts that the dominant eigenvectors of this matrix are span the so-called SDR space. And then people realize, well, there's nothing unique about the so-called M sur matrix. There are other matrices that also have this property, and some of them might actually be better because there are certain relationships that M sur is invisible to. So if y equals x squared plus x1, and x is distributed with a mean of 0. So if you have like a perfect symmetry in the regression function, and it turns out that M sur is blind to that. It cannot identify the perfectly symmetric components to the regression function. Now, usually you don't have perfect symmetry, but you lose power as you approach symmetry. And so Dennis Cook, who is probably the names at the University of Minnesota, Dennis Cook, probably the name most affiliated with this field anyway, came up with a whole bunch of additional so-called kernel matrices whose eigenspace would also span the so-called SDR space, but maybe in some cases would tend to span more of it than sur would. So sur is invisible to certain things. Cook came up with this thing called SAVE, which stands for sliced average variance estimation. I won't go through this in detail, but all SAVE is it's like sur but using conditional variances instead of conditional means. Right? So you still slice on y just as you do with sliced inverse regression, but within each slice, instead of taking the conditional mean of x given y, you take the conditional variance of x given y, and then you don't need to take the covariance anymore. You just average those. Right? There's a little bit more to it than that, but that's essentially the idea. So that was like 94 or so. There's this thing called directional regression, which has a very complicated kernel matrix, so I didn't even bother to put it on the slide. And then a very interesting thing is also was done by Kirchhoff Lee, who invented sliced inverse regression, is that it turns out that if you just take the triple product of y by x and x again, so y is a scalar, x is a vector. So if you take y by x transpose, so that's outer x by x transpose is an outer product matrix, but you weight it with y, the dependent variable. And then you average that out. That also produces the kernel matrix whose eigenvectors span at least a subspace of the SDR space, if not the whole space. None of these kernel matrices are guaranteed to span the entire SDR space in every possible scenario, but each of them will capture a good chunk of it. And there are even hybrid methods where people apply all the methods and then sort of take the union of their eigenspaces. But I don't know, I've never actually used that type of approach myself. In practice, it's more like an embarrassment of riches rather than worrying too much about what you got, and maybe this will come across more clearly in a minute when I transition to the examples. But usually, with a different decent sized data set, you'll have evidence of like 4, 5, 6 dimensions, and it's hard to make sense of more than 2 or 3 dimensions. So you're not worried too much about what you've missed. You're trying to make sense of what you got. At least that's my experience.
Without getting too much into bad form and explicitly talking about G, I would like to know, is G unique, or are there multiple G's that satisfy the, I see.
So let me respond to that. So first off, it's not bad form to talk about G after you've estimated B.
Okay.
It's totally fine to talk about G after you've estimated B. What you don't want to do is you don't want to tangle up those estimation sets. You don't want to require a preliminary estimate of G in order to have an estimate of B, because
It's not necessary.
then you worry about robustness. What if you misspecify your estimate of G? How does that interplay with your estimate of B? So you want to have an estimate of B that doesn't depend on G, but once you've got B, capital B is what I'm talking about here, this matrix here, then it's perfectly fine to estimate G. And this actually really is important historically, because this was the main argument that people made back in the early 90s, that this was the perfect adjuvant to traditional local polynomial regression. Because people saw the recursive dimensionality, traditional local polynomial regression only works if you happen to have, say, 2 or 3 covariates. But what if you can reduce your data to 2 or 3 dimensions from the original, say, 10? Then you can just apply local polynomial regression. Now, as to whether G is unique or not, the answer is it's unique modulo the basis you choose for B, which is inevitable. Okay, so fast forward now to like 2005, 2010, 2015. What I think happened after the initial like slew of activity around this methodology is that everyone thought it was kind of neat and clever, but no one like really used it in practice. I think I have to admit, no one used it in practice. And there may be different reasons for that. But one reason is that there wasn't all of this sort of ancillary stuff that you need to do statistical analysis for science, like can you come up with a p-value, can you do a hypothesis test, can you put a confidence band around something? Well, it's very hard to put a confidence band around a subspace, although people have tried. But formal statistical inference was a big gap. And essentially nobody touched this until like 2000. So a lot of the more recent work since 2000 has not been trying to come up with yet more and more kernel matrices that capture yet another corner of the SDR space, but rather to try to come up with tools that one can use to do formal statistical inference. And this work has progressed at pace, but has largely been unnoticed except by people who are actually working in the field, which I think is kind of too bad. So there's essentially 2 natural inference questions that arise in dimension reduction regression. One is, what is the dimension? How many real or true directions are there in the SDR space? So that's an important one, and there are tests for that. And the other is a so-called formative inference, in which you essentially say, are there sort of nested towers of matrices like this, such that you might be able to include something like Y, it's independent of the 1 transpose X given D2 transpose X, if I got this right? So you got like a larger collection of variables, and then you got a subset of those variables that you view as essential, and another subset of those variables that you're not sure belong there or not. And can you assess whether or not the extra stuff that's in D2 but not D1 is actually unneeded? Right. So that's almost like an F-test in regression, right? So it's essentially like an F-test for dimension reduction regression. So the methodology for doing dimension reduction and regression F-tests is only emerged, like I said, between 2000 and 2010. Where I'd say is largely complete now. So now that those techniques are here, we should no longer use that as an excuse for not using these techniques in real work. Okay, so I won't get into the details of that. Instead, in my I'll try to wrap up like in less than 10 minutes. Like I said, what I really wanted to do today was to focus on case studies, but because the methodology is unfamiliar to everyone, there was no way to avoid giving at least an introduction to the methodology. So I have 2 case studies, both drawn from NHANES. I think probably everyone here is familiar with NHANES. It's my go-to data set for illustrations. So there are 2 case studies, both from NHANES, but they're completely different in other ways. So the case study 1 is about blood pressure. So I happen to have a collaboration with some people in the school in ISR, so we've spent a lot of time thinking about blood pressure for the last 5 or 6 years. So we're looking at blood pressure is measured in anything. So in this case study, we're looking at blood pressure as an outcome in relation to predictors of blood pressure, demographics, and then all these so-called anthropometric type variables like leg length, arm circumference, and so on. Okay. So this is our blood pressure is our Y, of course, it's a quantitative variable, and all of these variables are X's. So the question here is, can we A, understand whether all of those explanatory variables are needed, or can we boot them out? And then once we've whittled the explanatory variable set down to the core essential ones, can we actually understand the form of this regression function? Can we learn something about the manner in which these variables are related? So with respect to the variable selection, you can form some natural hypotheses here. For example, you could say, well, what we have here is we have some demographic variables, we have some core anthropometric variables, and then we have some very detailed anthropometric variables. So you might ask, are the detailed anthropometric variables ignorable? Like once you know someone's weight, height, and BMI, you really need to know their arm circumference and hip circumference and so on. Okay. So that's the first test here. Is essentially asking, can I drop those detailed anthropometric variables? And if I drop them, am I confident that I'm losing real information? So with the coordinate test I talked about earlier, you get a p-value of 0.09. So there's no strong information, there's no strong evidence that you lose real information when you drop these detailed anthropometric variables. But there is strong evidence that you lose information when deleting anything else. So I didn't try every one of the 2 to 10 possible subsets here, but pretty much any other effort to reduce variables, you reject the null that there's no information in the variables that you dropped, right? So essentially what we end up with here is a model that only focuses on these with the 5 variables, excluding these other so-called detailed variables. And so that now, because we did it rigorously with this coordinate test, is a statement that you can take to the bank, basically, as much as you can take any other statistical hypothesis test to the bank.
It's a little surprising because BMI, height, and weight are not linear combination. But
Right. So I'm not sure I actually tested whether you need all 3 of them. I didn't, is that on here?
No, but if you have, it looks like if you have 2, you're saying you still need the 3rd one. Because it says you can't get rid of height or weight or
Yeah.
BMI. You gotta keep.
Yeah. So that's true. In a non-parametric sense, you don't need all 3. Fair enough. I need to think about that. I would think about it now, except we're running short on time. So then you can ask, well, what is the structure of this regression relationship? We're just going to restrict ourselves to the 5. What is the structure of this regression relationship? And basic question is, how many directions do I need among those 5 to capture all the relevant information in those 5? So that leads to a so-called dimension inference task here. And we can use different methods and different ways to infer the dimension. Long story short, we can get anywhere from 2 to 4, which is not too bad of a range, depending on which method for estimating the SDR space you use and which method for testing the dimensionality of the SDR space that you use. So I'm going to go with 3, although I'm really going to struggle. You'll see this in a minute. I'm really going to struggle to make sense of the 3rd direction, but I can confidently make sense of the first 2 directions. So I'm pretty confident that this is not a single index model like we discussed earlier in the presentation.
So the numbers there on the left are the dimensions that it says were necessary, 2, 3, 4,
Yeah.
etc. Okay.
Yeah. So it could have been as small as 0. It could have been as big as 5, but we got 2s, 3s, and a couple 4s. So sometimes I like to talk about how this, I didn't have as much time as I'd hoped to emphasize this, but I like to talk about how dimension reduction regression relates to some of the other maybe more popular techniques for flexible regression analysis, including additive modeling, generalized additive modeling, and nowadays deep learning and neural networks. But it does have this kind of neural network-like structure to it, in the sense that what we're doing is we're saying that we've got a certain number of directly observed variables, but we believe that we only need to take a limited number of linear summaries of those directly observed variables. And then finally, those linear summaries combine non-linearly to predict blood pressure. So the G function that we've talked about so much today is over here. The G function takes your variates to your outcome. And then each variate is itself a linear function of the observed explanatory variable. So everything over here is linear. Everything over here is nonlinear. It must be nonlinear because if say variant 1 and variant 2 linearly predicted blood pressure, then you could just collapse variant 1 and variant 2 into a single linear variant. And you can't do that because the inference methodology said you need all three of them, right? So that's not exactly what happens in a neural net, of course. In a neural net, both of these steps are nonlinear. In our case, this is linear and this is nonlinear. And an interesting thing is, if you think about what a GAM is doing, I can't help by saying this now because I mentioned it, is that a GAM is exactly the opposite. So in a GAM, it's the first set of connections that must be nonlinear, and then the second set of connections must be linear. So dimension reduction and regression and GAMs are almost exactly the opposite in that sense. You either start with a linear and then go to nonlinear, that's dimension reduction and regression, or you start with a nonlinear and then go to linear, that's GAMs. With the asterisk that the nonlinear transformations in GAMs has to be coordinate-wise. You have a separate transformation on each of the covariates. You can't combine them because then you'd get into the curse of dimensionality, which is what you always start going back to here. Okay, so what do we get when we apply this regression technology to the enhanced blood pressure data with these five variables filtered through 3 variants, right? So this is what I really wanted this talk to focus on, which is interpretation. I guess I need like 2 or 3 hours to do that. So one thing you can do to interpret these dimension reduction regression fits is to study the marginal relationship between Y and each of the factors or each of the variants, right? So the font is a little bit small, but this is a scatter plot of Y on variant 1, Y on variant 2, Y on variant 3. Now this, in a sense, isn't the right thing to do, because these things combine non-linearly, so it doesn't make a lot of sense to look at them marginally. But just if you do, what you see is that there is a meaningful linear or monotone increase between blood pressure and score 1, but with respect to score 2, it's almost dead flat. Okay. Now, blood pressure, you probably know, is an extremely noisy measurement, right? So you don't expect like a perfect, beautiful 0.9 R squared line, because people's blood pressure just fluctuates a lot from moment to moment. Okay. So a more sensible way to look at it, because again, there's a mandatory interaction. These variants must interact, right? So you have to find what that interaction is doing for you. Okay. So here's the trend curve from low S showing you what does blood pressure look like in relation to score 1, but stratifying on the values of score 2. And I'll talk about this in a minute in some detail. And here's a plot showing the fitted blood pressure against score 1 stratifying on score 3. I'm not going to say as much about this. Right. So what this is basically saying is that score 2 plays a role in modifying the relationship between the outcome variable and score 1, right? So it's a modification type of story here, is that the score 2 modifies the relationship between Y and score 1. So now let's see if we can't drill down a little bit further and figure out what score 1 is all about, and then later on we'll see what score 2 is all about. So the way I would do that is I would essentially look at the relationship between score 1 and each of the observed variables. Sorry, I didn't realize how small this text would be. This says female, male. This is age, BMI, weight, and height. So the thing that jumps out at you here obviously is this middle, right? Score 1 is heavily influenced by age, right? It's almost entirely influenced by age in a sense, and it's extremely linear and extremely homoscedastic. It's just like a very tight, clean measure of age, right? Now, you know, there's a lot of interest nowadays in talking about things like biological age and so on. So we can almost say that this factor is capturing your blood pressure age, right? It's the age that, it's the contribution of your age to your blood pressure, right? As your age goes up, there's going to be an increasing relationship between age and blood pressure, right?
This is where the doctor can say you look 30, but you're really 50 inside.
Unfortunately, it doesn't. I think so. The axis labels are so small, but unfortunately, the 30-year-olds are over here and the 50-year-olds are over here. I was actually going to make this point. Now, a single 50-year-old is as even as high as the worst 30-year-old. The best 50-year-old is worse than the worst 30-year-old. So I'm very sorry to report that as someone who's 51 years old, but it's sadly true. Now, what this is telling us how this blood pressure age, as I'll call it, relates to your calendar age or your actual age. But then the other half of the story is, how does blood pressure age relate to actual blood pressure? And that's where score 2 comes in. So I'm going to skip this in the interest of time. So score 2 turns, well, let me say one thing, is that these scores are uncorrelated. right? So score 2 must be uncorrelated with score 1, it must capture something unrelated to score 1 in the original data. Right? That's how the algorithm works, is that the scores, like in PCA or in factor analysis, the scores are uncorrelated. Well, they're not always uncorrelated in factor analysis, but what is score 2? What is score 2 based on in a sense? Well, there's a huge sex difference here. These are females, these are males. There's some overlap, but there's a huge difference in the medians and even beyond the medians, right? And other stuff comes into play here as well, especially BMI. So score 2 is a function, is uncorrelated to score 1. But as we saw earlier, score 2 modifies the manner in which score 1 relates to blood pressure. So what I'm going to argue here is that score 2 is the sensitivity to the blood pressure age, whereas, as I said earlier, score 1 is the blood pressure age. And again, I just have to keep driving home the point is that this really isn't necessarily a two-dimensional relationship, or at least everything in the data is suggesting this is necessarily a two-dimensional relationship. People will ask when I try to explain this that, well, isn't it just that the method has failed, that score 2 is an adjustment to your biological age, and I should like add 1 or 2 years to your biological age based on your value of score 2. Well, if that was the case, then score 2 and score 1 should have collapsed down to a single factor. Right? So
So
score
it means that some body types are more sensitive to blood pressure age and other body types are less sensitive.
right, exactly, right. And unfortunately, it's not necessarily clear which one you want to be. I may end up wrapping up the discussion on this. So what being in the less sensitive group means is that you have, at a given biological age or blood pressure age, you have higher blood pressure when you're younger, which is not good, and lower blood pressure when you're older, which arguably is good. And these are mostly the males. So if you just do like a basic regression analysis, blood pressure on age and sex, you'll find that men have a higher intercept, but a lower slope. Women have a lower intercept, but a higher slope. So younger women tend to have lower blood pressure, but older people, actually it goes the other way. When females have higher blood pressure than males. There could be something like a survivorship bias there. It's not necessarily that people's blood pressure has flipped. It's more that the men with very high blood pressure unfortunately have died. So sensitivity to blood pressure age simply means that you have a higher slope here. And I have a caveat in one of these slides. I just want to make this caveat, as we all know that NHANES is a cross-sectional study, and I'm interpreting it as if it was longitudinal. So there could be like a birth cohort effect. Right? It could just be that the 80-year-olds in 20, this was from 2017 or something, the 80-year-olds in 2017 were born in the 40s, I guess, and the 30-year-olds in 2017 were born in the 90s. So you can have, without stitching together multiple birth cohorts, you can never be sure that this is something we do a lot in other work I'm involved with, but they didn't bring that complexity in here. We can't be sure that what we're seeing here is a birth cohort effect versus an actual age effect. I think there's a very strong age component to it, but there may also be some residual birth cohort stuff going on as well. Okay, so I'm way over time. I had another small example, but I don't even think it's that important. Let me just review what I just said, and hopefully we can just have a little bit of discussion. So by using this somewhat unwieldy, in some people's minds at least, dimension reduction regression methodology, we learned a lot more than you can easily learn with ordinary least squares. We learned that there's some kind of essential two-dimensionality, maybe even three-dimensionality, but like I said, I will have trouble with clear factor there. But there's at least an intrinsic two-dimensional relationship between blood pressure and this particular variable that we've chosen to look at. And that if you make enough plots and think about things hard enough and stare at things long enough, you can actually wrap a story around these two factors that emerge. And the story is that one of them seems to refer to something like an age-dependent contribution to blood pressure, but that there are different demographic groups. I can't talk about within people differences, I can only talk about between people differences here. But there are different demographic groups for which the sensitivity to that biological age is either exaggerated or attenuated. Okay. All right, let me leave it there, and I'm happy to talk either in this group or informally with people who want to stick around.
Will this talk be focused?
The slides?
Yeah.
Yeah, sorry, I should have said this. I'm happy to give these slides to anyone. What's the best way to do that, Chris? Just,
So if the recording has worked, these slides are on the recording.
but they're all
I think the ones you got
in some
through.
cases, yeah. No, you can email me, Barry, and I'll just send, anyone can email me and I'll share you the slides. And also I should mention the code is available. This is all a lot of this is taken from the course that I teach. The code is on GitHub, and I can just give you the URL.
The other question I had is, what sample size do you require for these?
Great question. So clearly it's gonna need more than ordinarily squares, right? Very highly parametric methods will give you more precise estimates with your on target while I'm looking at it. And, but I don't think it's any worse than say factor analysis or principal component regression. It has the same sort of innate, what's the right word, power as say factor analysis. So I know that's not an answer, a direct answer to your question, but you can, this has a huge sample size, this is any has a huge sample size, but I use this. I was just doing some power analyses actually earlier today with like 200 observations and 8 variables in one file. The signal has to be strong enough to poke the noise. What's interesting is that the first direction always comes out super strong. And the hard question is there a second index? Is there a second uncorrelated component that contributes nonlinearly to the response? And sometimes there just may not be, or sometimes it's there, but you don't have enough power to find it.
And the different tests hint at something else additional, like you saw those other
Right.
ones that maybe 4.
There could be as many as 4. Not necessarily, one thing I didn't mention maybe very clearly is that some of these could contribute not to the mean, but to the conditional variance, or to like a conditional temporal or something like that. We're not just talking about the mean here, I'm only looking at. So yeah, I think the third dimension, I sort of have a sense about what it does, but I can't articulate it well enough in public. Yeah, the doctor, and the fourth dimension, it's even real, I don't know.
Is the GitHub code, is that R code or is that Python?
So the GitHub code is for a course I teach in which I try to do everything in Python, R, and Julia. It doesn't have exactly the same. These slides were actually made in Julia, but something very similar could be done in Python or R.
Because I looked and I saw packages that come up in a search and mainly I see R packages, but I didn't find Python packages.
In Python, it's inside of the stats models.
Oh, okay.
And Julia is just on my.
And have you found any problems with some of the ones that are public domain packages, the one maybe that you haven't written? Yes.
Yes, I'm sorry to say, yeah, the core estimation machinery is fine. You can fit the models, no problem. Some of these tests, one of the tests I think is implemented incorrectly, and I've been trying to get in touch with that. It's a little bit of an unfortunate thing. Dennis Cook was leading the charge on this for so many years. He's like, he's still around, but he's like in the 80s now. So I emailed him and asked how I can get it. They used to get students maintain all the packages, but I haven't been able to get through them. There's a bug that needs to be corrected.
Not quite, yeah.
It's only a special case, probably.
You mentioned a couple times, this is all cross-sectional, are there obvious extensions to longitudinal data structures?
So yeah, there's longitudinal, there's survival. And I didn't, the last case, the second case study that I didn't get to was for multivariate Y. Yeah, time series survival, longitudinal, multivariate Y. This is essentially like a marginal regression, like GD. So if you analyze longitudinal or time series data with this approach, you're still estimating marginal, focusing on marginal structure. There's no, I don't know, like a random effects way to do like within subject analysis. But yes, there are ways to calibrate the inferences to repeated measured data.
Seemed like the SIR technique relied on binning, slicing.
Yeah.
And I'm not clear if the PhD or other ones, were they based on binning as well?
Yeah, I went through that so fast. So
Well, you don't have to be, I just was curious if they're all based on binning.
no, they're not. So the PhD one is not. I actually really like it. No one ever talks about the PhD one, but I really like it. It doesn't depend on me. It's a moment. It's just like the third order moment of y by x by x. So this is a p by p matrix. So you're taking like, if the y weren't there, this would be like the sample covariance. But it's like you're taking a weighted sample covariance weighted by the dependent variable. I think that's extremely interesting. And somehow it's Stein's lemma. The proof that this works is not obvious. It's Stein's lemma. The eigendirections of this matrix span at least part of the SDR space. And then I like this one precisely because it requires no binning, so you don't get into an argument about how many splices to use. But the more commonly used ones, SIR and SAVE, the S in both of them is precise.
And then as a practitioner, do you often run several of these and see how much they agree and then?
Yes. In particular, you expect like a containment relationship where SIR is a subset of SAVE. It's a little more complicated than that if you have a lot of data because save is like, how do I put it? It can find more of the SDR space, but at lower power. So if you have a small sample size, save can give you less than SIR, but for a large sample size, save will almost always give you everything SIR gives you plus some more, because it's able to see things that are invisible to SIR. So if, yes, in practice, that's right, although with small sample sizes, the containment relationship won't be there.
Do you know anything about the actual dimension of that space compared to what the tools are giving? Like the actual dimension of the space is like less than twice the dimension, or is there some sort of bound that?
Well, like, it would be a bound in probability, like, you can never know anything in statistics with 100% certainty. So like the dimension testing procedures I use, they control the probability of overstating the dimension, not the probability of understating the dimension. So you can be like, if the stated dimension is like 3, you can be 95% confident that the true dimension is not more than 3, but you don't have a clear bound or control over whether the probability that the true dimension is less than 3.
Okay.
So it's conservative in a certain way. It's not clear that that's the direction you want to be conservative in, because it's not exactly a classical hypothesis test, but that's the control that you have with these hypothesis testing based methods for the dimension. So you can be pretty confident of what you found, that what you found is real, but you can't be very confident about what you missed. Okay. Which is probably the direction you would want to be conservative.
So who do you yak with to interpret all this stuff? 'Cause it's really something to interpret it. I think.
So one of the things I say, and maybe this is just what's the right word, like copying out of it, but is that it's not that these procedures are hard to interpret, it's that reality is hard to interpret, and these procedures are just giving you a more accurate view of reality than, say, least square. Like, why is a linear model easier to interpret? Because you just say, well, each variable has a single effect associated with it, and you tell a story about each of the effects. Well, what if that's not the way the world works? What if the world works non-linearly? What if it works both non-linearly and non-additively? Right? And then you're stuck fitting a regression model with a bunch of like say quadratic terms and interactions in it. And then I don't think you're in a harder place there than we are here. So it's really the world reality that makes things hard, not the methodology. I think we were talking about this earlier today in the CSCAR meeting. I mean, if you really do want to fit a neural network to data in order to accommodate the presence of nonlinearities and interactions, then you want to do science and interpret the structure of the neural network, that's going to be even harder than this. Yeah.
The interpretability is so hard.
Yeah. At least this gives you factors, like in factor analysis, as like the core estimate. And then the hard thing is to talk about how those factors are, and those factors are uncorrelated with each other. And then much harder thing is how are those factors related to the outcome.
And do you think domain expertise helps in interpreting, or maybe not? Or is it good to have a fresh mind?
Well, I think so. Yeah, this is interesting. I just finished teaching a class on like statistical communication for master's students. So, you should. What I tell them is that you should be able to present the results of your fitted analysis, whether it's a dimension reduction, regression, or whatever, without any domain expertise at all, because you're making statements about additivity, linearity, interactions, conditionality, and so on, conditional independence. All of those concepts are purely statistical concepts. So I don't need to know anything about what these variables are to tell you that certain variables are uninformative once I've conditioned on others, or that some variables contribute additively and others contribute non-additively, or some contribute linearly and others contribute curvilinearly. So all that discussion can happen completely. I'm not advocating stopping there, but all that discussion can happen short of bringing in any domain knowledge, and it probably does need to happen first. And then once you've established like what the core like geometry of the regression is, then you want to, of course, you or recruit someone to help you make a story around it. Right? So I tried to do that. Very rushed here, but I tried to do that with the blood pressure example. I tried to first say, let's say it's a two-dimensional structure. Let's keep that third factor out of the picture for the moment. It's a two-dimensional structure. there's a very strong monotonic linear contribution of the first factor. And what the second factor does is essentially modify the manner of that, the structure of that linear
But it
relationship.
sure helped me on, when you said blood pressure age, that
Mhm.
helped me understand or think that I had a better idea
Right,
of what's going on.
And
That-
most people think in terms of the world rather than purely from mathematical abstractions, but I think you can aspire to understand what's going on purely like geometrically and then layer the science on top of that.